Welcome to this explainer. Today, we're diving into a really fascinating royal mystery, one that can literally only be solved using the power of mathematics. We're going to be walking through a high-stakes puzzle that brilliantly unpacks an entire chapter's worth of concepts, specifically focusing on squares and cubes. It's just a fantastic way to see how abstract math concepts have real logical applications. Let's get right into it. So, we begin our story with Queen Ratnamanjari. The queen left behind a vast fortune of ratnas, which are precious stones. But to inherit this unbelievable wealth, her relatives actually have to solve a highly complex puzzle. She was kind of hoping her son Koisnam had learned enough about solving puzzles to secure the treasure. But, well, he's not the only one in the running. There are 99 other relatives invited to the reading of her will. And the stakes for Koisnam and those 99 relatives? Absolutely massive. The Queen's will states that if all 100 answer at the exact same time, they share the ratnas equally. But here's the catch, and it's a big one. The first person to solve the problem gets to keep the entire massive fortune all to themselves. So yeah, it's a total winner-takes-all race of the mind.
Section 1. The 100 Locker Puzzle. The rules of the game.
Okay, so picture this. A minister assigns each person a number from 1 to 100. Person 1 goes down the line and opens every single locker. Person 2 then toggles every second locker, meaning they close it if it's open and open it if it's closed. Then person 3 steps up and toggles every third locker, the third, sixth, ninth, and so on. Just imagine the sheer chaos in that room as each person goes down the line, changing the state of the locker doors based strictly on the multiples of their assigned number, all the way up to person 100.
So, after all 100 people have taken their turn, the doors that happen to remain open will reveal the code to the safe. But here is the amazing part. Before the process even begins, Koisnam realizes he already knows the answer. Seriously, how did he figure it out so fast without anyone even touching a single door?
Section 2. The secret of factors. Counting the toggles.
Koisnam realized that he didn't need to physically watch all those lockers opening and closing. He just needed to count how many times each locker door is touched. For example, think about locker number 6. It's touched by person 1, person 2, person 3, and person 6. Mathematically speaking, 1, 2, 3, and 6 are the exact factors of the number 6. So the number of toggles perfectly matches the number of factors. Pretty clever, right?
And this brilliantly illustrates the core mechanism of the whole puzzle. Locker number 6 has 4 factors. Because 4 is an even number, the door is toggled an even number of times. Open, closed, so it ends up closed. But look at locker number 9. It's only touched by person 1, person 3, and person 9. That's 3 toggles. Because 3 is an odd number, the locker goes open, closed, open, meaning it remains open.
Section 3. Unlocking square numbers. The partner factor.
So, the crucial point here is that to find the open lockers, we just need to identify which specific numbers have an odd number of factors. Most factors come in partner pairs that multiply together to make the number, like 1 and 6 or 2 and 3. Because they come in pairs, most numbers have an even amount of factors. But square numbers? They completely break this rule. Because a square number is expressed as a product of a number with itself, one factor doesn't have a distinct partner, like 6 times 6 to get 36. That 6 is just counted once. That leaves square numbers with an odd number of factors.
The math perfectly proves the theory here. Locker 1 only has one factor, so it stays open. Locker 4 is a perfect square, 2 times 2. It has 3 factors, 1, 2, and 4. So, yep, it stays open. Locker 9 has factors 1, 3, and 9. It stays open too. Ultimately, only the perfect square numbers will be left wide open at the end of those 100 turns.
And boom, there's the safe's code. By identifying the 10 perfect squares between 1 and 100, 1, 4, 9, 16, 25, 36, all the way up to 100, we've essentially cracked the code to the Queen's massive inheritance, right alongside Koisnam. How cool is that?
Section 4. Decoding perfect squares, spotting the patterns.
Now that we've solved a royal puzzle, let's look at the broader mathematical properties of these perfect square numbers, because they're fascinating. Perfect squares have strict rules that make them highly predictable. For one, they will always end in the digits 0, 1, 4, 5, 6, or 9. They will literally never end in 2, 3, 7, or 8. This means you can quickly figure out if a number is completely disqualified from being a perfect square just by glancing at its units digit. Also, if a perfect square ends in zeros, it will always have an even number of trailing zeros. Like if a base number ends in 3 zeros, its square will end in exactly 6 zeros.
We also see a really strict rule of parity here. The square of an even number is always going to be an even number, and the square of an odd number will always remain an odd number. It's this wonderful mathematical consistency that really helps us check our work when we're making large calculations.
It's also crucial to remember that the square root is the inverse operation of the square. And when you're working backward, every perfect square actually has two integer square roots. For instance, the square root of 64 isn't just positive 8. It's actually also negative 8. Why? Because mathematically, a negative 8 times a negative 8 equals a positive 64.
Section 5. Exploring cubes and roots, adding a dimension. Up to this point, we've pretty much mastered two-dimensional mathematics through squares. But let's level up. What happens when we jump into 3D space? If squares represent the flat, 2D area of a shape, what mathematical concept represents the physical, 3D volume of an object?
Well, by adding a third multiplier, we move from finding area to finding volume, creating what we call a cube number. So instead of just n times n for a flat square, we're calculating n times n times n to find the volume of a three-dimensional cube.
And as you can imagine, cubed numbers grow significantly faster than squares. Just look at the progression here. We rocket from a volume of 1 to 8 to 27 to 64, and suddenly we are all the way at 125 in just 5 steps. The addition of that third dimension causes some serious exponential visual and numerical growth. Now, just like with our locker factors earlier, cubes have their own hidden architectural rules beneath the surface. If you break a perfect cube down into its prime factorization, you're going to find that every single prime factor must appear in matching sets of 3. It is a perfectly balanced mathematical structure.
I'll leave you with this final puzzle straight from our source material to ponder. Look at the massive spaces that develop between consecutive cubes. If you subtract 66 cubed from 67 cubed, is that difference greater or smaller than subtracting 42 cubed from 43 cubed? Exploring these massive expanding gaps between consecutive cubes will completely change how you view mathematical growth and three-dimensional space. So, what do you think? Keep exploring, and I'll catch you next time.